In this video, we're going to be looking at question number 6 on page 600 in your textbook. And in this question, it's very similar to the lab that we do in Chem 30, where we do a redox titration. One difference is that we're using dichromate instead of potassium permanganate. So we're using potassium dichromate in this example instead of potassium permanganate. But both of those solutions are not possible to make a primary standard. So even though you might try to get the exact right concentration from a solid, it's not possible to get that within the precision that we need for it to be a standard solution. So our first step is going to be to do a standardizing titration. So we're going to use this solution, which is the same solution we used in our lab, or will use in our lab. And we're going to use that solution to standardize the potassium dichromate, and then they're going to use the potassium dichromate to find the concentration of acidified tin 2 chloride. So there are two sets of titration evidence, so you actually get two tables here. In our first titration, we have 10 milliliters of 0.05 mole iron 2 solution, this whole thing, with potassium dichromate. Now, it says the potassium dichromate solution is first standardized by titration with 10 milliliters of acidified solution of the primary standard. So we know this concentration. Before we can get going on that, we need to actually pick the oxidizing agents and reducing agents. So this is all going to be aqueous when dissolved in water. So you're going to get iron 2, we're going to get sulfates, we're going to get ammoniums, which will be just a spectator. We're going to have more sulfates, we're going to have water, both because it's here as well as it's in an aqueous solution. And we're going to get potassium ions, we're going to get dichromate ions, and we're going to, because it's acidified, they're going to give you hydrogen ions. In your lab, we use sulfuric acid, which gives us the acids. Now, the iron 2 is in our data booklet, and it is both acts as a reducing agent as well as an oxidizing agent. So oxidizing agent on the right-hand side and reducing agent on the left-hand, or on the right-hand side, sorry. And so it's both an oxidizing agent and a reducing agent. Water is also an oxidizing agent, a reducing agent. Potassium ions are an oxidizing agent, but they're terrible. And this is kind of a common mistake. People assume that potassium ions, because they're at one end of the table, are really good at something, but they're not. Potassium metal is a wicked reducing agent, but it is not a good oxidizing agent when it's in its ionic form. So we also have sulfuric acid is an oxidizing agent, and it's a pretty good one. It's pretty high up in there, but the dichromate and hydrogen ions are the strongest oxidizing agent by a long ways. They're way up here at the top. And my iron 2s are better than water. So it's going to be iron 2s becoming iron 3 and dichromates becoming chromium 3s. So my strongest reducing agent is this, and my strongest oxidizing agent is that. And when I pick those two half reactions, I come up with this balanced reaction here. So I took the dichromate becoming chromium 3s and the iron 3s becoming, this should be iron 2s becoming iron 3s, and then I balanced using the electrons. So here I had dichromates are 6 electrons, and we had 1 electron here, so I had to multiply the irons by 6. And that's how I came up with my balanced half reaction. Now I have a volume of 10 milliliters of the iron 2 solution and 0.05 mole per liter concentration, because that's what they made to standardize the dichromates. The dichromates, we calculate their volume from the table, and so I'm going to subtract 2.3 from this to get 11.5. This is 10.6, this is 10.8, and this is 10.7. So I know that the volume of dichromate is the average of these three, because they're within 0.1 of each other. So 10.6 milliliters plus 10.8 milliliters plus 10.7 milliliters divided by 3. So it's going to be 10.7 milliliters is its average volume. Now we're just into a straight titration. So I can find the number of moles of iron 2 ion that are reacting, because the number of moles is C times V, so it's going to be 10.00 milliliters times 0.0500 mole per liter, so it's going to give me 0.500 millimole. And then I can get the number of moles of dichromate because I know the coefficients. And so I've got one dichromate, so I'm going to take 0.500 millimole from this. I'm going to, because that's the number of iron 2s, I put the iron 2s on the bottom, and I get one dichromate going here. And this is going to give me my number of moles of dichromates. So I take 0.5 divided by 6, so I get 0.0833 millimole of dichromates. And then I can calculate the concentration of dichromates by taking the number of moles, so 0.0833 millimole, divided by the number of milliliters. And the number of milliliters of dichromate were 10.7 milliliters. So I get 0.00788 mole per liter, or that'll be 7.78 millimole per liter, same thing. Now this is now the concentration of my dichromates, so I can use that for the next one, because now I've got iron, is that from a different one? Oh, maybe screwed. So I'm going to be able to use that for my next titration set of data, which is here, where I've got the 10 milliliters of tin 2 with dichromate. And now I know the concentration of this is going to be 0.00788 mole per liter. I'm going to be able to calculate the average volume for the tin, or for my dichromate from this data table. And I need to get my balanced reaction. Again, I'm going to have tin 2 ions, I'm going to have potassium ions, I'm going to have dichromate ions, I'm going to have waters, and I'm going to have acid particles. So this is going to end up being my strongest oxidizing agent, this is going to be my strongest reducing agent, and I use those to get my balanced reaction, and I just do another titration calculation. So you go through the same step of sequence. You'll know the volume of dichromate, you know its concentration, so you can calculate the number of moles of dichromate, use the coefficients to find the number of moles of tin 2, and then finally you calculate the concentration of tin 2, and that's your final answer to the question. Now, I'm not going to go through that whole process again because I've just done that with the previous example, but we made there was a primary standard of iron solution, iron 2 solution, use it to standardize the dichromate, use the dichromate to then find the concentration of tin 2s. So that's how you would approach that question. The key difference in redox titration is that we have to find the major entities, select the strongest oxidizing, strongest reducing, balance their half reactions to get a net reaction. And then the one other thing to be aware of is that dichromate is in your burette, and dichromate has, I believe it's an orange color that's listed at the back of your data booklet, and so those orange drops are going to disappear. So for your dichromate, the strong, potent orange color is going to disappear, and at the end point, you're going to have one drop that remains, and so it's going to make a pale orange solution color.